So here's the solution that was prepared beforehand, and you will see I've used different symbols for these speeds. If you remember, we said that the speeds were W, D, and R, but in my presentation just now, I used different symbols. So this BW is the velocity or the speed, walking speed, W. And this is the car speed, VC, and this is the riding speed. But I used driving, D for driving, W for this, and that, because it's much easier to type W, R, and D rather than these. Anyway, but you'll see at the end, these were the answers, if you remember, 3 and 3/4, 7.5. 10, those were the V's, and we also had the speeds. Um, the speeds were, yeah, this was the speeds. And the A, B, and C, oh, what happened to the A, B, and C? Um, Something happened. I think I deleted the A, B, and C. All right. Okay, let's not worry too much about that. Let's get on to question 7 now. Right, there it is, question 7. Question 7 says, a 4x4 table is given. Just ignore this stuff on the right-hand side. That's part of the solution. There's a question is on the left-hand side. The letters A and B are each written in the table twice. So you've got a grid like this, 4x4, and you write A twice and B twice, as you can see here. But there are conditions. Each cell in the table will contain at most one letter. Well, I suppose that's obvious. You're not going to put A and B in the same thing, right? But the second one is important. No row or column will contain two identical letters. In other words, you can't have two A's in the same row or in the same column. Likewise, you can't have two B's in the same row or the same column. So here you can see they satisfy all these conditions. So the question is now, in how many different ways can the table be filled? Well, so this is a counting problem. And we have to fill in 4 of these 16 squares according to the rules which were mentioned. So let's fill in the A's first. Okay, so what do? You have to choose, to fill the A's, you have to choose 2 separate columns because you can't put the 2 A's in the same column. So we'll choose 2 separate columns. As you can see in this picture here, I've chosen second column and the fourth column. Okay, now let's just take a particular choice, like what we have done, and ask how many ways can you fill the A's in these? Well, you can fill the A in any one of these 4 spaces. But once you fill the A, you cannot fill the B in the same row. So there are only 3 ways in which you can fill the B's. So in this case here, the A's can be filled. The first A can be chosen in 4 ways, the second one in 3 ways. Not allowed to choose the row in which that A appears. That makes 12. Now this is for this particular choice, for this choice. of two columns. All right, now we've chosen the columns 2 and 4. So the next thing is that there are many ways in which you can choose two columns. So, apart from this choice of columns, now this is, I'll say 2, 4. Right? We have, okay, in how many ways can you choose 2 from 4? Okay, I think you've seen this thing before, but we'll actually list them here because we don't have so many. We can put 1 and 2, 1 and 3, 1 and 4, right? Okay, now you say, okay, let's ignore 1, 2, 2, 3, 2, 4, and then finally 3, 4. So there are 6 ways in which you can choose 2, and the 2, 4 is the one that we just chose here now. But apart from that, there are 5 others. All right, so altogether there are 6 ways in which you can choose 2 columns. All right? For each of these choices of 2 columns, each of these 6 choices of 2 columns, we have 12 ways in which the A's can be filled. All right. So therefore, there are 72 ways. So there are 6 times 12 equals 72 ways of filling the A's. All right. Now, we'll just hold on with that. I'm going to rub all these things out. We're going to say here, A's can be filled in 72 ways. All right. Now, what I'm going to do now is I'm going to choose one particular choice, one of these 72 choices. And for that choice, I'll try to see how many ways I can fill the B's. I've chosen this particular one here. So what we have here, there are 72 of them. I've chosen this particular one. So there's an A here and there's a A here. Right, now I want to choose 2 B's. Right? Okay, now I'm going to choose 2 B's, but now once the A's have been filled, we have to be a little bit careful here. Okay, I want to choose, let's take a pair of columns. Take columns 1 and 2. Right. Now, this particular column has got the choice, this choice is 1 blank and 1 filled. See, 1 blank and 1 filled. Now, for that particular choice, I'm going to calculate the number of ways I can fill B's in these 2 columns, right? So, let's start. Suppose I put a B here. I'm only looking at these 2 columns. I can't put a B here because you're not allowed to put 2 B's in the same row. I can put a B here and I can put a B there. That is already filled. So you have this 2 for that choice of B. Okay, let's go down. Let's take the next choice of B. Suppose I've got a B here. Okay, I'm not going to worry about the A. So suppose I've got a B there. Right. In this case, I can put another B here. I can't put a B here. I can put another B here. So that makes another 2. Right? Okay. So let's take the B now in the 3rd column. 3rd row at least. So suppose there's a B here. And here I can put a B here, here, as well as here. Right? So there are 3 choices for B when B is in this position. And then finally, when B is in the last position, if I put a B here, then I can put a B here, I can put a B here, but I can't put a B there. So there's another 2. So when you got the choice for 1 and 2, this gives you 9 possibilities. Right. Now, there are 9 when we have 1 filled and 1 blank. Now, what are the other choices for 1 filled, 1 blank? Now, the 1 filled, 1 blank columns are 1 blank and 1 filled. Choices are, okay, we had 1, 2. Right. Now you could have 2, 3, 1 filled, 1 blank. Or you could have 3, 4, 1 filled, 1 blank. And I think I could have had 1, 4, 1 blank, 1 filled. Now remember, there were 6 possible choices of these columns. Right. But in each of these cases, we have 9 possibilities. So in these cases, we have okay, there are 4 of them. So for each of these, you've got 9 possibilities. So you've got 36 possibilities. So we've taken care of 4 of those 6 possibilities in this column. So just bear that in mind. Now, there are 2 more. The ones that we didn't consider are where you got both blanks, 1, 3, and both filled, 2, 4. Right? Both blanks and both filled. All right. So let's take each one of them and count. We've got 36 so far. We've got 2 more to go. So let's look at the 1, 3, both blanks. How many ways can you fill those? So let's just uh, look at and we're looking at these 2. Okay, let's put a B here. I can't put a B here, but there are 3 here. Tick, tick, tick. Right? Now, you will agree that for each choice of B, I've got 3 here. If I put B here, I'll still have a 3 here, because both are blanks, you see. There's a B here, I'll have 3 choices. B here, I've got 3 choices. So altogether, you've got, there are, the B's can be chosen in 4 ways. And for each of those 4, you always have 3 possibilities. So there are 12 altogether. So that takes care of 1, 3. And the only thing we're left with is 2, 4. And so when you choose that pair, 1, 3, we see that there are 12 possibilities there. Now we're going to take 2, 4. Now this is the case where both are filled. All right. So let's choose a B here. Now remember, we are doing 2 and 4. So if I go to B here now, I can't fill there, but I can take that. That. I can put B's anywhere here. Okay, so that's 3. Let me take that out. If I put a B here, if I put a B here, I can't put a B here. So these are the only 2 possibilities. So you go to 2. When I go to B there, and then there's one more situation, and that is when the B is here. So you can put yeah, we are doing 2, 4. So you can put a B here, you can put a B here, but you can't put a B here. So there's another 2 here. Okay, so that takes care of all the possibilities. So in this case, I've got 7. All right. So what do we have? We have that for this particular configuration, so for this choice of A and A here, we had 9, and we had 36, right? That's for those 4 pairs of columns. And the one where both were empty, we had 12. And when both were filled, we had 7. That takes care of all the possible pairs of columns, right? And altogether, we got 36 plus 12 is 48, plus 7 is 55. So there are 55 possibilities in this particular situation. take out all these things, because what we've solved the problem for this particular choice of two A's. Now remember, for this particular choice, there are 52 or 55 ways in which you can fill the two B's. But there are 72. There are 72 of these. So for each one of them, there is 55. Because I fixed a particular choice and I calculated for that one. So therefore, there are 72 times 55. That's 3,960 possibilities. If you want to know how I got 3,960 so quickly, I multiplied 72 times 5, and then I divided this by 2, multiplied this by 2, I must get the same answer. And that gives you 360. I multiplied that by 11 now. It's easy to multiply 36 by 11. 3 plus 6 is 9. And there we have it. No calculators. So these are all short methods of multiplication. Okay, so that's the answer to question 7. Let's just check to see. You see, I got a long story here, but I think I've unpacked this thing here. It's to be quite honest, when I was reading the solution which I had written some time ago, I couldn't understand it. Now I've explained it nicely, and I hope you can follow it. It's much better to look at the solution which I just gave you rather than this. This is not a better solution. Okay, that's question 7. Let's go down to question 8. Now, question 8, it's here on the left-hand side. Don't worry about that for the moment. Right. What does it say? It says that 3 straight lines cut triangle ABC into 4 smaller triangles. So you can see the one straight line here from C, one straight line from B, and A, and one straight line from B, and these triangles are identified. The areas of the 4 small shaded triangles are each equal to 1. So all these areas here are equal to 1. Area of this is 1, this is 1, that is 1, that is 1. Now they ask, determine the total area of the 3 quadrilaterals. Okay, the quadrilaterals are the white parts. You can see each of them has got 4 sides. So you want to know what is the total area of the unshaded part. Now, I can tell you that I struggled with this. It's not an easy problem, but it's a very beautiful problem. There's a lot of interesting geometry that comes out from here, especially about areas. So pay careful attention, because there are many important ideas regarding areas feature in this problem. And I'm going to discuss each of them quite fully. Now, before we start, I want to look at this result here. In fact, I can call this a theorem. I didn't know this theorem. I found it's a very interesting theorem. It says the following. It says that if you got DE is parallel to BC in a triangle, like the way we got it here. All right, so you got one pair of a line segment which is parallel to one of the sides. Okay, so that's what you got there. And then you join BE and join DE. They intersect somewhere. Now, that's all is given. This is parallel, and this is joined and is extended to meet BC. And this is a beautiful result which I didn't know. And BG is equal to GC. This line here actually bisects the opposite side. Now, the thing about this problem here is not easy to prove because it uses a important result in geometry. I'm not going to discuss this result, but it's a well-known result for people who study geometry at a higher level. It's called Serva's theorem. I think it's Cheva. He's probably a Spanish guy. Now, Serva's theorem is an interesting theorem. It says if you got three in a triangle, if you draw a line from the vertex, one of the vertices, to any point on the opposite side, this is called, it's given a name. It's actually named in honor of this guy who's got this theorem. It's called a Serbian. Because this guy discovered such a beautiful theorem, they've named this line here, any line, which goes up to the side, they call it a Serbian. Now you can do this for another side as well. Take another Serbian, but actually you take three Serbians. But you take three concurrent Serbians. Once you draw the third Serbian, then the two Serbians, they intersect at a certain point, right? And you take the third Serbian that goes through the point of intersection, right? So if you got three concurrent Serbians, then he came across, he discovered this very important result. Suppose D, E, and F are these Serbians, AD, CF, and BE. Then Serva's theorem says that, watch, AF over FD, let's start from here. AF over FB, I'm sorry. Multiply, now you start from B. BD over DC. Keep going in the same direction. And BD over DC. And now from C, you go back to A. CE over EA. If you multiply these three ratios, you're always going to get one. Very beautiful result. See? You can try it out. Take any triangle and draw three concurrent Serbians like this. Measure these six sides, multiply these three ratios, and you will definitely get one. So that's Serva's theorem. So just bear that in mind. I'm going to delete it. And I'm going to use it in this situation that I've got here. So according to that, you've got BG, let's start with B. BG over GC. I want to show that BG equals GC. So BG over GC, right? Go up CE over EA. times AD. From here, you come back to B. AD over DB. This is equal to 1, according to Seber's theorem. Right. Now, there's another very important result, which is in the school syllabus. It's called the mean proportion theorem. It's in your syllabus when you do similar triangles in grade 11 or grade 12 or somewhere. The mean proportion theorem simply says if you got any line parallel, any line segment parallel to a third side, then these sides are in the same proportion. In other words, the ratio of this to this is the same as this to this. That's a mean proportion. Right? There is another result on similar triangles. In fact, you use this mean proportion theorem to prove a very important result on similar triangles. Similar triangles are triangles which have got the same angles. And so if you've got two triangles having the same angles, then the sides are in proportion. You can actually use this theorem that I just said. You've got a parallel line here. This over this equals that over that. Right? If you can prove that, then this I'm just going to say this as an aside. I don't need it. But this, if you take the small triangle, it's got the same angles as the big triangle. And you have, there the ratios are, this side in the small triangle is opposite this one. Those angles are equal because they are corresponding angles. So AB over this entire thing, well, it's not AB here, but this length here over this entire length, because the side of the large triangle opposite the same angle dot is this length here. So this over this equals, now these two angles are the same. So the corresponding sides are this over this is equal to that over the whole thing, just like what we had there. And finally, the remaining angle, those two ratios are equal to this over that. Now people can sometimes mix up. They say this over this is the same as that over that. That's wrong. This over this, right, is equal to that over the whole line. And that is equal to this over the whole line. Because the small triangle is similar to the large triangle. Right? This over this equals this over this is a mean proportion. But what I just told you now is about similar triangles where the sides are in the same proportion. Anyway, to get back to what we are saying here, so you can see this line is parallel. So I've got the AD over DB mean proportion. AD over DB, because this line is parallel, is equal to AE over EC. Right? So AD, this over this is equal to AE over EC. So what I'm going to do is I'm going to replace this AD over AB, right? I'm going to replace that by AE over EC. So let's just rub that AD over DB out here. And we just said that's the same as AE over EC. Lo and behold, AE cancels, CE cancels. BG over GC is equal to 1. So BG equals GC. That's what you wanted to prove. See, but to prove this, you needed Server's theorem. Maybe that's one of the reasons why I didn't know this result, because it uses a result outside school geometry. But this is a very nice result. Okay, so just bear that in mind, because we haven't even started yet. We've got a long way to go to calculate the white area here. And you will see how far we are by looking at the next diagram. Look at that one. So many things I have to use to eventually get to the answer. All right, so this was the question. You need to calculate the white area. I've got a small picture here. This we have used many times. When you got a single Serbian, I can call this a Serbian now, a line joining the vertex to a point on the other side. The Serbian divides the opposite side in a certain ratio. So you got BD over DC. That's the ratio. Yeah, BD over BC, ABC. That ratio, this over this, is the same as the area of that shaded triangle over the area of this shaded triangle. So these two ratios are the same. BD over that equals the area of this over the area of that. It's very easy to prove. I've said this many times, but in case some of you have not seen this before, the area of this over the area of that is half BD times the height of this triangle over half DC times the height of this triangle. But these two triangles have got the same height. So the heights cancel, the halves cancel. You'll end up with BD over DC. You can try it out. It's very easy to show that BD over DC, I can't see the C that's in, is the same as the ratio of the areas. So that's quite important. Right. This one here we've already spoken about. Now here, this result is another useful result in areas. If you got a, let's just call this A, B, C, D. Now suppose you know, say on BC, you've got two triangles. You've got BAC, the BDC. Both have got the same base, right? But the third vertex are different. But suppose you know that these two triangles have got the same area. Area of ABC, suppose you know that, is equal to area of DBC, right? Then, just think about it. They both got the same base, they got the same areas, so it means they've got the same heights. Because the area of this triangle is half base times height. So if they got the same height. Oh. So if you draw the height here, and you draw the height here, these two are the same, right? And they are parallel because they are both perpendicular. So you got two equal sides. They're also parallel. So those four vertices form a parallelogram. Basically, what we are saying is that then this AB is parallel to AD. And AB and D. Then you have that AD is parallel to DC. So if you got the same area, then those points there when you join them, that line will be parallel to this. And conversely also, if this is parallel, then they got the same area. Because then in that case, you know they got the same height, they got the same base, therefore they got the same area. Right, so we're going to use these results. Just remember this one here, and this one here, and that one, to solve this problem, which is far from trivial, as I've already said. Okay, so let me just take this thing out. All right, now what I'm going to do is I'm going to go to my original picture. This is my original picture, but it's not exactly the same, but it's a similar kind of a thing. All right, so you got these 4 triangular areas, and you got these 4 quadrilaterals, the white piece, and I need to know what the sum of the whites are. Right. Now, there are lots of constructions we have to do here. And you'll see in this case here, what I've done is I joined these two and I'm going to focus my attention on this triangle. That red triangle, right? Now you will see that you've got 3 Serbians, right? Very similar to what we had earlier on. But what's interesting is that if you concentrate on this thing here as your base, and if you join these 2 lines, join these 2, and if you look at the triangle with C, okay, we don't have a name for this point here. We can call it H or something. If you focus on the triangle BCH, and you've got this line, you got that line, and you got both these are the same area, and you add this white area here to both of them. You'll have white plus yellow equals white plus yellow. Both of them are the same area, which means that you are in the situation here. You got HCD, that area, equals HCK. Let's call this K. And we are in the situation here. You got the same base, and you got this area equal this area. So I've got that area equals that area because it's 1 plus shaded area equals 1 plus the same shaded area. So this area here, same base, and these 2 points give you the same areas. And then we concluded that this line is parallel to this. See? So we can conclude that this line is parallel to this. Right, now we are in the situation here. Because now we have a triangle, the same thing, BCH, right? And you got one line, this line here is parallel to that. And we saw that whenever you have this situation, and you take A, join it to where these 2 diagonals intersect and extend it, these 2 are equal. So in this situation here, there it is. I got that this is parallel to this. Take this point, join it to the intersection, produce it. Then these 2 here are now equal. right? I'm just going to take out all these things here. What we've got here now is that I've just proved that these two lines are equal here. Or let me use black. Because we applied this last theorem to this triangle here. We know that this line is parallel. I've taken that out now. And therefore, when you join this, these two will be equal. All right. Now focus your attention on another triangle, which is very similar. But this time you focus on this one here. A, let me draw this in red also. So you got A, G, so can you see the small triangle here? All right, with the three red sides. Now you'll notice that this is almost exactly the same as the previous one. You got that joint, these two are equal, and therefore this 1 plus white area equals 1 plus white area. So therefore this area here that I'm pointing to is the same as this area, which means that according to the previous result, that HF is parallel. If I join H and F, even this is parallel to this. For almost exactly the same reasons. But I'm not joining this and extending it as I did before. I'm just concluding from here that since these areas are the same, then this line is parallel. Now we have an interesting situation where we now look at this triangle here. Okay, I've got these two lines are parallel, but now I look at this triangle here. C, H, F, right? I'm looking at this red triangle here. This is the midpoint of CH. We just proved it. And you have that this line, which is a part of this line, is parallel. So you got that this line is parallel to this, and these two are equal. And now the midpoint theorem, or the converse of the midpoint theorem, kicks in, which says that the third side is bisected. CG equals GF. So you have I'm going to write down CG equals GF. And just remember that this G here is the midpoint of the Servian, CF. And that follows because of the converse of the midpoint theorem. And to prove the midpoint theorem, I had to prove that this is the midpoint of that. It took me a while. And I had to prove that this line is parallel. And also now that took me a little bit while. And then we have come to this final conclusion. Well, it's not yet final. CG equals GF. Right, so now I go to the next diagram. Oh yes, there's another important thing here. You see, when you got a median of a triangle, if D was the midpoint of the side here, then these two areas will be the same, right? Because we said the ratio of this over this is the same as the ratio of that is to that. That area is to that area. So if D is the midpoint, then this ratio is 1. Both of them are equal. So that ratio is equal to 1. So these two areas are the same. So a median divides an area into two equal parts, if this was a midpoint. That's an important result. So now, if you look at this little triangle here, this thing here is a median. So if this is x, so that is also x. Well, let's call it y. If these two, because this is the median for that small white triangle. So now you've got, but BG is a median for this big triangle. So it means that y plus 1 plus this is the same as y plus 1 plus this, because that's the other, this median here divides this large triangle to two parts, that one, and that has got the same area as that one. These two have got the same area, these two have got the same area. Therefore, these two have got the same area. Right, the point about this is that when you join the diagonal of the white quadrilateral, that diagonal starting from the vertex, from the corner of one of the vertices of the large triangle, right? Then this area is bisected. We just said that this area is the same as that area. So if the white area that you're looking for, suppose this white area is X. Uh, okay, whatever it is, these two are equal areas. Right? I'm going to call it ZZ. That means that areas are the same. All right, just bear that in mind. That likewise, C, if I join C to this thing here, this area is halved. And if I join this to this area is also halved. So BG halves the white area, but the same thing should happen to that one because there's a symmetry about this. All these are, it's exactly the same kind of a problem. And that diagonal bisects that area. So just bear that in mind. Okay, so I want to calculate the sum of the three white areas. So I give a name X to that area, the white area. Right? So, oh yeah. You see, let's have a look at this. Have a look at this triangle. To put this in red again. Let's look at this triangle with the three red sides. Now, we just proved a little while ago CG equal to GF. G is the midpoint of CF. So AG is a median of ACF because G is the midpoint of this. AG is a median, which means that AG divides the red triangle into two equal parts. One part, its area is 1 plus x, and the other part, its area will also be 1 plus x because these two areas are the same. Right? The median divides the area, the red triangle, into two equal parts. This area is 1 plus x. Therefore, this other area, this part here, is also 1 plus x. So this is already 1. So this has to be x. That's a beautiful conclusion, that these two white areas have got the same area. Okay, which means that all the three have got the same area. All right, so that's quite powerful. And then also, we saw that this diagonal here, which I've drawn in this last diagram, it divides this area into two equal parts. The whole area is x. So this is x over 2, and this is also x over 2. Okay. And now this is x, and that is x. Okay. So the problem is to find x. And once you find x, the sum of the white areas is 3x. So now we brought it down to what is 3x? X plus x plus x. So let's try to find x. And we can do this again if we look at the ratio of AF to FB at the bottom. AF over FB. I'm going to use this one here. This over this is equal to that area over that area. Now watch, AF over FB is equal to, if you look at this triangle, okay, fortunately I've got, a color ink here, so we can focus very quickly on the triangle that I'm looking at. So many triangles that I have to look at. Now look at the small triangle here. AF over FB is equal to x over 2 over 1. X over 2 over 1, which is x over 2. But I'm just, for emphasis, I'm going to put down x over 2 over 1. All right? And AF over FB is also equal to, now this time I will wipe out all these things. Right? Now, we look at the large triangle. And we know that CF is a Servian. Look at the large triangle and CF. Now that is now a Servian, and we saw that A of F over FB will be equal to this area here. CF divides the large triangle into two parts, right? The left-hand part, AF, what is the area of the triangle ACF? Now you've got an X here. So that is 2x plus 2. Sorry, let me just put this in black. So AF over FC on the one hand is equal to this small white triangle over 1. We got that there. Now I'm looking at the large triangle. And there, the large triangle AF, x plus 1 plus 1. Those are the 4 areas that make up this triangle here. The left half of CF, and that is 2x plus 2. And then here, on the other side, CF, it divides the other part of the triangle that CF divides is this one here. So here, if you add up this, the areas, you got 1 plus 1 plus x, which is x plus 2. And at last, we have an equation involving x. Oh, this was not an easy problem, guys. But we have an equation involving x, and once you got x, we can work out 3x. Now let's see if this thing works out to a nice answer. Cross multiply, you got 4x plus 4. Cross multiply, it's equal to x squared plus 2x. X times x plus 2. Quadratic equation, x squared. Bring the 4x to the other side. Minus 4x. No, wait a minute. Plus 2x minus 4x. So it's minus 4x. Minus 2x. Minus 4 equals 0. Well, unfortunately, this doesn't factorize. So it's minus b. Right? Using the quadratic formula, minus b is plus 2. Plus or minus square root of b squared, which is 4, plus 16, 4ac, over 20. Now 2 minus square root of 20 is a negative quantity, so you must discard that because x is obviously a positive area. So dividing on both sides by 2, you get root 5. Because this is 2 plus root 20. Root 20, you can take out the 4 from there, you get 2 plus 2 root 5. Divide 2 plus 2 root 5 by 2, and you have 1 plus root 5. So this is 3 into 1 plus root 5. And ladies and gentlemen, this is the area of the white part. Oh, I don't know where these guys get these problems from. This is an IMO problem. Okay. But even if you didn't understand it, there are lots of little things here which are important things which I did to get to the answer. All these little results, this over this is the same as area of that. And this one here is an interesting one which I didn't know. This one here is an important one. We use the converse of the point theorem, right? And lots of results we used to finally get to the answer to this. Okay, so let's just get to the so you can see I've done this, but I've broken up this into several pieces. But right at the end, you will see, maybe you can't see it too clearly. You'll see here, 3 into 1 plus root 5. That's the answer. So but I've got all these lines all in the same diagram, which makes this thing very complicated because you can't keep track of the triangles in this unless you're an expert. Okay, so let's get on to the next problem, which is question 9. We've done so far, we've just done 2 problems. Okay, well, 8 problems. Now, question 9. A function fn is defined on all positive integers n. Very often you have this kind of a problem where you have a function defined on integers, right? And they come up in these competitions, and you must go and check all I've done quite a few of these types. Go and check them and try to get acquainted with the manner in which these things are done. There are certain techniques that you use in this particular problem. We have a function which is defined like this. Then f of 1, that's the image of the integer 1, positive integers. So what you've got is the following. You got the positive integers, 1, 2, 3, 4, 5, all the way up to n. And then you got a function which is defined on all positive integers. So 1 goes into f of 1, 2 goes into f of 2, that's a function. 3 goes into f of 3, and so on. Right. And to make life a little bit easy, we'd rather call this, give a name to this, because this gives you a sequence kind of a thing. Let's call this A subscript 1. And this one here, we'll call it A subscript 2, A subscript 3, and so on. So Fn is A subscript n. So we let f of n, or let's make it f of k equal to A subscript k. K can be any value, 1, 2, 3. So we rename it to make life a little bit easy. So in which case, our equation is, it's easier to read this equation like this. It's A1 plus A2. You could have called it term 1, T1, T2, and so on, because that's what you use in school. But generally, we don't have to put a T to describe the term. All right, so this is A1 plus A2 all the way up to AN. This dot, dot, dot means adding up all these things. And this is equal to n squared times A subscript n. Okay. Now they say calculate the exact value of f of 2024 if it's given that f of 1, so you know that f of 1, this one here, A1, is 2024. So you know the first one. And the question is, what is f of 2024? So let's just put 2024 somewhere here. That goes into f of 2000. So we need to calculate A 2024. All right, so this is, so in other words, we need to calculate the nth term given this. Now, you can do it like this because, you see, you got the sum of the first n terms. This is the sum of the first n terms is equal to this. So let's look at the sum of the first n plus 1 terms. So you got the nth term plus the next one, the sum of the n plus 1 terms. So the same formula works because for any n greater than 1, this formula works. So I've got n now is replaced by n plus 1. So you can put n plus 1 all squared here, and this is a n plus 1. So wherever I got n, I can put n plus 1, and that is what I got here. But now this part here, we already know is n squared times an from the top part. So, which means I just want to keep track. We need to calculate this. That's the question. What is f of exact value of f of 2024? Right, if you look at this now, what have I got? I got n squared times a subscript n equals, well, plus an plus 1 is equal to n plus 1 all squared times a n plus 1. All right. So we got a n plus 1 occurring twice here. Let me bring all the a n plus 1 to one side. So I'll write down n plus 1 all squared a n plus 1, right? That. Take the a n plus 1 to that side, and you're left with n squared a n on this side. So let's take out a n plus 1 as a common factor. The remaining term is n plus 1 all squared, which is n squared plus 2n plus 1. And I'm taking out a n plus 1 minus 1. Taking out a n plus 1 as a common factor is n squared a n. These ones will cancel. And here you have, this is n into n plus 2. So I have n into n plus 2 times a n plus 1 equals n squared a n. Now, the reason why we do all this is we can actually calculate n plus a n plus 1, the n plus 1th term, in terms of the previous one. We are almost there. This calculation involves an and an plus 1. So we'll try to work out what the connection between these are consecutive terms, an plus 1 and an, right? So we have an equation involving consecutive terms. We've got an plus 1. So this part here tells you can cancel the n's, one of the n's. You have n plus 2 times an plus 1. And this n cancels with nan. So n plus, I'm going to put an plus 1 over an. What is the ratio of consecutive terms? And that's an important thing to calculate. Right? The ratio of consecutive terms is equal to, well, I've got an plus 1 times n plus 2. So the n plus 2 goes to the bottom. An plus 1 times n plus 2 equals n times an. The n goes here. So when you cross multiply, it must come to this. So there it is. You have a very nice formula that works out the n plus 1 term into, the ratio of the n plus 1 term to the nth term. All right. So I'm going to sort of delete all these calculations here because all this actually came down to this beautiful formula where you got the ratio of two consecutive terms, which is an plus 1 to an. See, you can actually calculate f of 2, f of 3, and so on. Let me do that just to, I know that f of 1 is 2024. According to the formula, f of 1 plus f of 2, and when I add, now here I've got n equals 2. That will be 2 squared, n equals 2, you see, times f of 2. So you got 2024. Oh. So you have that this is 4f2. So 4f of 2, bring this to the other side, you get 3 times 4f2 minus f2 is 3f2 is equal to f of 1. So now you got f2 is equal to 1/3 of f of 1. See? Now if you try here, you put, so in other words, this a2 is equal to 1/3 of a1, which is saying that a2 over a1 is 1 over 3. So see, here if you look at n equals 1, then you have a2 over a1, n equals 1, 1 over 3. See, you got the answer straight away without having to do all this. See? And that this is for any n. So that's the beautiful part of this, where you're making a calculation not with specific numbers. Here we're only going up to f of 2. You can go up to f of 3, and again, you can work out what f of 3 is. But then it'll take you a long time to get to f of 2024. So now the question is, what is f of 2024? What is an? Right, so what you have to do here, here's the trick. We need to work out A 2024. That's what you got. A 2024. I'm going to take this ratio over A1 because I know A1 is f of 1. It's 2024. Right, but I'm not going to put 2024 here. I'm going to put, this is A2024. I know this ratio, an plus 1 over this, right? Now I have to multiply A2023 and make it 2022. Then multiply A2022 over A2021 all the way like that until you come to A2 over A1. Right? And now, you see, because we are dividing and multiplying, this cancels, and this one here would have canceled with the previous one. So you got A2024 over A1 on this side. Right? But we know this. What is this equal to? According to our formula, this is n over n plus 2. So this first one is 2023 over, that's your n, over n plus 2. So it goes to 2025. So this first part here is n over n plus 2. Now this one here is 2022 n over 2024. So it's n over n plus 2. The next one is 2021. That's your n, and you have to add 2 to that. until you come to A2 over A1, which will be 1, 1 over 1 plus 2. We actually calculated A2, A1 before, but if you use a formula, it's 1 over 3. So what do you have here? So this is 2024 over. Now at the top there, you got 2023 factorial. And at the bottom, you got 2025 factorial. But wait a minute. You don't have the 2 and the 1. So I have to multiply the top by 2 times 1. Right? So you have 2023 factorial, goes all the way up to 1. But that's okay. But 2025 factorial, it doesn't land at 3, it lands at 1. So if I multiply the top by 2 times 1 and multiply the bottom by 2 times 1, then I get that. Okay. Now, what is this? 2025 factorial is 2025 times 2024 times 2023 factorial. This, if you take the first two terms, you get 2025 times 2024, and then you have all the numbers from 2000. Now that's in the denominator. The numerator, I got 2003 factorial, 23 factorial, times 2 times 1. Sorry, we're running out of space here. Sorry to be so untidy, but let me just remove. I'm going to just rewrite this thing properly. On the left-hand side, I had 82024. That is what I was looking for. And I had over A1, which is 2024. I'm going to put that down. On the right-hand side, I've got 2000, I'll rewrite this, 2023 factorial times 2 times 1 all over 2025 factorial, which is 2025 times 2024 times 2023 factorial. Because from this point onwards, you'll have all the numbers going up to 1. And I did this purposely because I wanted this, it's a monstrous number, to cancel. And even the 2024 at the bottom cancels. So you're left with 82024. It's 2 times 1, which is 2, over 2025. Right. So you get a nice, lovely answer for f of. This is f 2000 and f 2024 is 2 over 2000 and 2025. Okay, so that's the answer, the 2024 term. Now let's just see what I had here. I had already worked this thing out. So final answer is 2 over 2025. Let's just get rid of all these things and get on to solution there. And there it is. Right, so in case you didn't follow what I said, you can have a look at this. It's almost the same thing, exactly the same thing, but written very much more neatly. Okay, the final answer is 2 over 2025. Okay, so that brings us finally to question 10. There are 10 problems in the team. Thank God, nothing more than that. So we come to the last question, which seems to be a geometry question. All right, so in this question, you got an triangle ABC. In triangle ABC, AB is equal to 6. So there's AB. So remember, AB is 6 units long. BC, this whole thing here, is 16. So you got two sides of the triangle. The 6, the 16. Now, they say the center O of the circle that passes through B, it goes through B and the midpoints of AB and AC. So the midpoints of AB and AC, AB and AC. All right, so this N here is the midpoint. You can see these are equal, and M is the midpoint of this. So you got a circle which contains the midpoint of BC, as you can see. It contains the midpoint of BC and also goes through B. Now, there's always exactly one circle that goes through 3 points. So through B, N, and M, there's only one circle which could go through. But they also say that the center, it belongs to the bisector of angle ACB. There's ACB, the center is also on the bisector of this angle. So in addition to going through the 3 points which are mentioned, B is one of the vertices of the triangle, N and M are the midpoints of 2 of the sides. So you draw the circle going through those 3 points, and that center actually lies on the bisector of this angle. All right, now the problem is to find AC. What is the length of AC? And let's not be fooled. We didn't say, oh no, okay, M is the midpoint of AC. So that's fine. So if I know MC, then AC is twice that. But I wanted to say that K, be careful, K is not the midpoint of BC. It might look as if it's midpoint, it's not. And don't assume that. So where do we start in this problem? Now there is a result. If a point lies on the bisector of an angle, there is a very important result. Let me just state that straight away. Whenever you got a bisector of an angle, then there is an interesting result which says that every point on the bisector, its distance from the two sides are the same. Every point on the bisector is equidistant from the two arms of the angle that is bisected. Now let's just put that into words. What we are saying here is that when you take this point here and you draw a perpendicular, that's the distance, and draw another perpendicular, then the important result in geometry, unfortunately these days people don't do all these things. If you got 90 degrees here, then the distance from here to there, the theorem says that these two are actually equal. The theorem says that it's not given. Those are equal. I'll put that in red. Right? Knowing that this is the bisector, these two angles are the same, It's given. Sorry. Okay, let's just. Sorry, I got stuck there a little bit. So if you got this as a bisector, uh, so we are saying that these angles are the same. If this angle is theta, so is that, and so the angle is bisected. Then these two triangles here are congruent. Why? Because you've got a common side. You got this angle equals this, that angle equals that. So you got angle, side, angle, and they're congruent, and therefore the sides opposite theta equal. So this is the theorem. So these are equal. And you also have, I'm going to use this, because these two triangles are congruent, you have that those sides are also the same. Right? Just bear in mind. Those two triangles are congruent, those are the same. So that, knowing that as a result, it's now natural to say that let's draw a perpendicular from here, from the center. This is a point on the bisector. So let's draw from this, draw a perpendicular to this, and then draw another perpendicular to this. And then remember, these are 90 degrees. Because they're perpendicular. We just said that these two triangles are congruent. So these are equal. Those two are equal. That's what we just proved. Right. So the other nice thing to draw these two things is because you also know, if you know your circle theorems, when you join the center of the circle, VK is a chord. When you join the center of a circle, if you draw a perpendicular to the chord, then this perpendicular bisects that chord. Right? That's also a theorem in geometry. All right, I'm going to just repeat some of these things now because I said too many things all at the same time. So let's get to the next diagram where I got all the pictures. Right. So this is what we are given. We were given that this is 6 and this is a midpoint, so you can make these 3, 3. We also said that O lies on the bisector. Okay, so that's what's given. And your problem was to find BC. No, AC. Remember, that's a goal. Now here I just said that if you got a point, the center joining this, like that, then it turns out that these two are equal because it's very easy to see it. It's a theorem in circle geometry. All you have to do is to join these like that, and these two triangles are congruent because these are radii, you see. These are radii, and you got a side is shared, so this side is common, and these two angles are 90 degrees. So this is a hypotenuse right angle side. So these two triangles are congruent, which means that this piece is equal to this piece. So whenever you drop a perpendicular to a chord, it bisects the chord. And conversely, if you take from there, if you take it, join it to the midpoint of this chord, then it's perpendicular. So both those things are useful. All right. So which means that in our situation here, This is what I've got so far. I've got that. I'm going to try to put them in red, all these conclusions. I like to put my conclusions in red, right? These two are equal because these two triangles are congruent. And then the circle theorems, one of the theorems says that these two are equal. I'm going to call this thing X. That's all right. We'll call it X. We'll call this X as well, right? Now, these two are also equal here. Let's call this Y and Y. Now, one of the things it's not easy to see, but we've got another pair of congruent triangles here. When I join OB and OM, and I look at these two triangles which have just been created, this triangle and this triangle, we just showed that this equals that, right? Because it's a point on the bisector of the angle, the equidistant. But these are radii. This line is equal to that line. And you got 90 degrees. So you got three things in this triangle equal three things, hypotenuse, right angle, and side. So these two triangles are also congruent, which means that since this line here is x, this y is actually equal to x. We'll take out all these things. So I've just shown that if this is x, that is x, then this part here is also x. Because if I join this and join that, you get two triangles which are congruent. I'm not going to clutter up this diagram. So this also becomes x. Because you got to, from the center, you got perpendicular. Okay, so that's very, very useful. Now remember, okay, I need to calculate AC, right? I know that M is the midpoint. So let's just call this point here, let's call this A, which means that this is also A. Right. So I've got a long line here like that, another long line here like that, and I've got a piece here, I've got a piece here, I've got X, 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 X. I've got a 3 on this side, and I've got a small piece on this side. So there are quite a few things which are known here. But before we go on, I want to look at this diagram here. There's another theorem in geometry which you don't do in school, which features very regularly in competitions, higher competitions. So you should know this result. If you got what you call secants, you got an A point outside the circle, you draw two lines, one line going up through this circle getting to the other side. You draw another one like this as well here. Now these are two random lines, ABC, ADC, right? Now, although they are quite random, there is a nice relationship between this. You can actually have that AB, the piece outside this long secant, you call this a secant, times the whole secant, AC, piece outside times multiplied by the whole secant, it remains the same no matter which point you take on the circumference, which means that if I chose D, then this product, which is the piece outside, times the whole secant, still the same, doesn't change. So you got lots of lines which are moving out like this. And in all these cases, AB times AC is equal to AD times AE. Now, what's the reason for that? I've drawn these two dotted lines to show you that you can prove it. So how do we prove it? To prove it, we use cyclic chord theorem. In a cyclic chord, the exterior angle, an exterior angle of a triangle, cyclic chord. You see now you got a cyclic quadrilateral, BCED, right? And this angle here is an exterior angle of the cyclic chord. So therefore, it's equal to an interior opposite angle like that. And likewise, if you take that with the double curve, this is also an exterior angle, right? It is supplementary to this angle that I'm pointing to. That angle is also supplementary to this. So those two are equal. That's the reason, right? These two are supplementary. They add up to 180. So 180 minus the one that I'm pointing to is not only equal to this, it's also equal to that. So therefore, these two are the same. But now if you look at this whole picture, you'll see that you've got the small triangle. It's got the same angles as the large triangle. So you have triangle ADB. ADB is similar to triangle A. I'll leave A there because A is in both triangles. But D is double curl. So in the large triangle, double curl is C. AC, E, right? So ADB, B is single curl, and the last symbol will have to be where the single curl is. Now, once you got this, I can take my ratios without having to look at the picture. AB, see, similar triangles, you must name them properly, like what I've done now, right? You name them according to the angles, the side opposite the angle, equal angles, you have to put them in the correct positions. So you've got AB, we need AB. AB over first third over AE, first third. What else do you need? Well, you've got AD. AD sitting here. So it's AD, that's first second, over first second. AC. Those triangles are similar. So the sides are in the same ratio. And now if you cross multiply, AB times AC, there it is equal to AD times AE. There it is. Right. So similar triangles give you the result very beautifully. Okay, so this is an important result. A piece outside times the whole thing is equal to, it doesn't change, right? It's always equal to a piece time outside times the whole thing. All right, so bearing all that in mind, I now can try to prove that, try to calculate what AC is. Okay, now I call this A. Now I'm gonna do this for this point here. A is outside the circle, so you will have AN times AB, AN, piece outside, times the whole thing, equals AR, that's a piece outside, times AM. Remember, we are going up to, the secant is going all the way, crossing the thing, going to the other side, cross this and get to the circle again. We stop there. So it's AR times AM. Now, AN is 3, and AB is 6. And AR, now what is AR? Can we work it out in terms of x's? Now, AR, oh yes, of course, it's equal to AM minus RM. AR is AM minus RM times AM. Now, AM is A. M is the midpoint, you see. We need to calculate 2A. M is the midpoint, we call this A, so the whole thing is 2A. So we need to calculate this A. This is where I'm getting to. So AM is A. RM, we said, is 2X. And we have AM. Or AM is A again. Right. So you got A into A minus 2X A into A minus 2X equals 18. Oh, you got two unknowns, A and X. So this is not going to help us too much. But we know, we haven't used the fact that BC is 16. BC, it was given that BC is 16. Remember, this was 6 and BC is 16. Now, I just want to record this somewhere and rub everything out. What I've done here is calculated. Wasn't very neat about it. I got that A into A minus 2X equals 18. Right. Now, BC is 16. Let me just put 16 equal BC. Now, BC is the same as X plus PC. It's that plus the whole thing. Now, remember earlier on, I told you this triangle here is congruent to this one here. So PC is the same as QC. QC. But QC we can see is going to be QM plus MC. So it's X plus A. So this is X plus A. So that is A plus 2X. X plus A. So A plus 2X is A. A plus 2X is 16. So I'm going to write this thing down. So to summarize, what A plus 2X is 16. I'm just going to put this underneath this other place because I've got an A minus 2X there, you see, which is nice. So I've got an A plus 2X is 16. Right, now why don't I put A minus 2X? That's nice. I've got A plus 2X. A minus 2X is 18 over A. If I divide on both sides by A, and now I can get rid of the X by adding. And lo and behold, I have only A's left. And that gives you an equation. You know, solving equations is not a plain thing. Eh? You have to look at a lot of things simultaneously. So I've got two equations and two unknowns. But I've got an unknown, the same unknown on this side. But when I add the x's, I have 2a equals 16. I'm sorry, 16 plus 18 over a. One equation, one unknown, multiplied by a, again a squared here, 16a plus 18. You got a quadratic, and you can cancel all the 2's. So you have a squared minus 8a minus 9 equals 0. Bring everything to one side, divide by 2, and blissfully this thing factorizes, unlike the other example where you had square roots and all that. There's a minus 9 into a plus 1 equals 0. A minus 9, it factorizes. So a has to be 9, can't be negative 1, because a is a length, you see. So if a is 9, 2a is 18. So the answer to this question is 18. Right? And it's not easy because we used this very important result here to get one equation, and somehow we got another equation, and we manipulated those two equations to get to my A. All right, so that is quite a demanding thing. We eventually got A equals 9, and if I look at my solution that I had, there is. To AC is 18. Right. So I've got a long story here, but if you didn't follow some of my story, you can check out this one here. Okay, that takes us to the end of the 2024 team paper. As you can see, it's a hard paper. 10 questions. They make it very hard because there are 10 people who are all tackling the same questions, and maybe they can put their heads together, they can get to some solutions. But I must say, I would be very surprised if any team got even 8 out of 10, because these questions were quite hard. All right, so that brings us to the end of this, and thank you very much for listening. And don't forget to look at the other ones. We've got lots and lots of discourses like this, and this one was a very long one, but you can always stop and take a break and come back. But we've got solutions to a large number of questions set by the South African Maths Foundation, whose website is www.samf.ac.za. Right? When you go to their website, you'll see all the question papers. This W is really W, UU. W again, W dot SAMF, South African Mathematics Foundation, dot AC dot ZA. That's your website. If you go there, you'll find a lot of information, all the question papers for many years, but we are looking at only the question papers in 2023, 2024, 2025, and we have a number of questions, exams, which are competitions which are held in that year, and we go to the end of that. We do all the problems there, except round 3, the Olympiads. I don't do that one. Okay, because the full solutions are given on that web page for that one. Okay, so enjoy the rest of the day or the evening, and thank you for listening.